Welcome to EDU World Space.
This is chapter 21, problem number 62. We're given a dipole moment of positive E and negative E. They're separated from each other by 0.68 nanometers. And they're embedded in this dipole is embedded in an electric field. The strength is 2.2 times 10 to the power 4 newtons per coulomb. And in part A, we're asked to calculate the dipole moment P. So that dipole moment P is going to be equal to Q, the amount of charge that a single charge has in this dipole, times how far they are from each other, right? So in our case, it's positive E, so it's going to be 1.602 times 10 to the power negative 19 coulombs times 0.68 nanometers would be 10 to the power negative 9 meters. So the dipole moment is 1.09 times 10 to the power negative 28 coulombs meter. Now in part B, we're asked about the torque. What is the torque when dipole is perpendicular to the field? So P is perpendicular to the electric field, and in this case, we're asked to calculate the torque. So from the definition of torque, it's the cross product of P and E. So PE sine theta is going to give us the torque. Since we calculated P, 1.09 times 10 to the power negative 28 coulomb meters. And we have the electric field strength 2.2 times 10 to the power 4 newtons per coulomb. And we have sine to be 90. As you know, sine 90 is going to give us 1. So the torque is going to be 2.4 times 10 to the power negative 24 Newton meters. In part C, we're asked torque again, but this time the angle between P and E is 45 degrees. Well, the torque again equals PE sine theta. Pretty straightforward. 1.09 times 10 to the power negative 28 coulomb meters and 2.2 times 10 to the power 4 newtons per coulomb. This time we're going to have sine of 45 degrees. Then the torque is going to be equal to 1.7 times 10 to the power negative 24 Newton meters. Now in part D, we're asked the work required to rotate the dipole from being parallel. So the initial case, the dipole is parallel with respect to E, which means the initial angle is 0 degrees, to the work required to rotate dipole from being parallel to the electric field to being anti-parallel to the field. So then in the final configuration, the angle between P and E is going to be anti-parallel, means 180 degrees, right? P is, let's assume P is up, then the E field is down. In this case, E field is down, P is down, right, in the initial case. So the work done is always the negative of change of potential energy of the system, right? Change of potential energy of the system means final potential minus the initial potential. From here, since we have a negative, then we have the final potential negative of it plus the initial potential. Then the final potential, the potential energy in terms of the dipole moment and the electric field is actually the dot product. So negative PE cosine theta final in this case plus PE cosine theta initial, then is going to give us the work done. So let's rearrange this. P times E, then cosine initial minus cosine final, right? So P, let's plug in before going there, let's figure out what cosine initial would be. Cosine initial would be cosine 0. Cosine 0 will give us 1, right? Minus final 180. Cosine 180 is negative 1, but there's one more negative in front of it, so this becomes positive. So 2 times P times E gives us the work done. So 2 times The dipole moment was calculated in part A to be 1.09 times 10 to the power of negative 28 coulomb meters, and the electric field was given to us as 2.2 times 10 to the power of 4 newtons per coulomb. So from here, the work done would be 4.8 times 10 to the power of negative 24 joules.